Okay, water tank has the shape of an upright cylinder. There we go. The cylinder is filling at a rate of 1.5 cubic meters per minute, and the tank has a radius of 2. And at what rate is the water level increasing when the water is 3.2 meters deep? So we have a cylindrical container, and inside that container, when you pour water into it, the water also takes the shape of a cylinder whose radius will match that of the container and whose height will just increase steadily as the container fills up. So we're measuring the volume of a cylinder of water shaped like this, whose radius is 2 and whose height is changing all the time. So what they're giving here is a volume rate, which means we need some way of talking about the volume of a cylinder. Volume of a cylinder is volume equals pi r squared h. So the volume is increasing. In this case, because it's a cylinder, the radius is 2 meters all the way down. So this radius is actually a fixed amount, and the variable is just our height. So there are two ways to handle a cylinder with 2 letters in it, and I'll show you the easier one first. And like I say, the easier one is because R is fixed at 2, it's 2 no matter where you are or how full the cylinder gets. We can treat this like it's just a constant. We can say volume is pi times the radius is 2 forever times h, so our volume is 4 pi h. And now we can differentiate that and get dv equals, our variable is h, so 1 times 4 pi h to the 0 dh. And if we want a derivative with respect to time, we divide both sides by dt. And there we are. dv dt is our volume change, which is 1.5 cubic meters per minute. 4 pi is a constant, and then we have dh dt, which is how fast the water level is changing. If this is in cubic meters per minute, this will come out in meters per minute. And we should be able to solve for that. dv dt is 1.5 equals 4 pi dh dt. Divide both sides by 4 pi, and we get dh dt is 1.5 divided by 4, also divided by pi. I get 0.119 meters per minute, or about 12 centimeters per minute. So that's the change in the depth. It's positive because the water is getting deeper as time goes on. Now, in this case, we were lucky that the radius was fixed. If you're in a cone shape or something like that, then the radius is not fixed. And if you want to be able to handle both measurements changing, we can do that. Pi r squared h. I'm just going to reset this and do the derivative. This is the more complicated way that always works. You can think of this as a product where you have pi r squared times h. And if it's a product, you can differentiate it using the product rule. So here's the improved version. The derivative of v is dv. And on this side, I have to do first times derivative of second, which is dh, plus second times derivative of first. And the derivative of this piece is going to be 2 pi r dr. Okay, just product rule, first d second plus second d first. Now, if we want a time derivative, we divide everything by dt. And this is a more powerful formula because it can handle changes in anything. If your volume is changing, there's a place for that. If your height is changing, like the water's getting deeper or the cylinder's stretching upward, there's a term that handles that. And if the radius is changing, if your cylinder is expanding somehow, then you have a term that can handle that as well. You can plug in values for all these things and solve for any one of these derivatives. So if you know that one of these values is going to be constant all throughout the problem, then great, take advantage of that. But if they're not, implicit differentiation means you can do it anyway.